Hey everyone, welcome back to Probability Theory. This will be lecture 27 of the course, and in this section we're going to touch on the gamma probability distribution. So let's go ahead and jump into it. We'll call this section 3.5, the gamma probability distribution. So we've looked at the normal probability distribution already, and so with the normal probability distribution we said the density function looked a bit like this, right? You've got your mean in the middle, and what's really important to note here is for the normal the distribution is symmetric. So the distribution is symmetric, right? Symmetric about the mean, right? Meaning it's kind of a mirror shape. And when we said at the time that this was bell-shaped. So some random variables that you'll encounter are not going to be symmetric like this. So some RVs are, so 1, not symmetric. Okay, and then 2, not they don't have valid values below 0, so they're non-negative only. So no non-zero, or no values less than 0. Right, and so this is going to give rise to distributions that have a bit of a right skew. They're kind of skewed to the right. And so what do we mean by that? Well, a typical distribution like I'm describing might look like this. Right, so this certainly is kind of mounded like a normal distribution, but in this case we might say the mean is way over here. Right, so in these examples, like kind of most of the data is to the left of the distribution, and there are fewer examples as we move to the right, and this is 0. And right, so this is all the negative values here. Notice there's no density there. Right, so this is a typical sort of distribution. This is the typical sort of shape for something like a gamma distribution. Now, there are countless examples, right? Countless examples of random variables in nature that might kind of look like this. One of the things that I like to point out is this idea of the length of time between engine malfunctions. Okay, so this is an example of something that's typically sort of gamma. It's got like this right skew. Right, so normally the length of time between engine malfunctions is going to be kind of centered around something here, but occasionally you'll have periods of time where you'll have examples where there's long periods of time. You'll have these outlying values, right? So something like way out here, but those are going to be few and far between. Most of the time, components are going to malfunction around something over here, but occasionally you're going to have examples that are far to the right. Now notice you're never going to have negative values, right? So, and this is a perfect example of the distribution being sort of cut off here, censored, if you will, at 0. So no values below 0. Okay, so let's go ahead and define a gamma distribution. And this is going to be one of the ugliest density functions you're ever going to see, but it's a good one still. It's very useful, and it's actually not too difficult to work with. So a random variable, y, is said to have a gamma distribution. Okay, it's said to have a gamma distribution with parameters alpha greater than 0 and beta greater than 0 if and only if the density function is equal to, so it's y raised to the alpha minus 1 power times e to the negative y over beta power, all divided by beta to the alpha times, and this is a gamma this is a gamma symbol, evaluated at alpha. And this is for all positive values. So 0 less than or equal to y less than or equal to infinity, all positive values. And it's going to be 0 otherwise. Okay. All right, so this is really the important part here. Okay, now this is not a complete definition yet because this is a function itself. So this is called the gamma function. And what is that? And so we'll say where gamma of alpha is equal to the integral from 0 to infinity of y raised to the alpha minus 1 power times e to the negative y dy. Okay, this is called the gamma function. Okay, so this is a kind of wild distribution, right? So you've got y raised to this parameter, e raised to the random variable divided by another parameter, the parameter raised to the parameter, and then you've got this function evaluating this other parameter alpha, right? So you've got kind of a little bit of a mess here. Let's focus in on the gamma function for a second. Let's talk that through. What is the gamma function? Okay. Now, the gamma function is an integral. It's not a difficult integral to work with. But when you're identifying the distribution, it's important to know what this parameter alpha is and to calculate this gamma function. So let's just do a couple examples here just to see what this looks like. So what is gamma of 1? Well, it's going to be equal to the integral from 0 to infinity of y raised to the alpha minus 1. So remember, alpha is 1, so it'll be 1 minus 1 times e to the negative y dy. Okay, and so this, of course, is 0 to infinity integral e to the negative y dy, right? And so when we integrate this, it's negative e to the negative y from 0 to infinity. Okay, and now how do we do this? Well, we have to use, the old limit as b approaches infinity of negative e to the negative b minus negative e to the negative 0. Right, so that's just evaluating the bounds. And of course, this is going to go to 0, and this will go to 1. So this would be 0 minus negative 1, and so you get 1. So the gamma function evaluated at 1 is 1. What about the gamma function evaluated at 2? Well, it's going to be real similar, right? It's just going to be y to the 2 minus 1 e to the negative y dy. Okay, and so that's just 0 to infinity of basically y e to the negative y dy. And so if you recall your calculus 2, you can use integration by parts to do this. So remember integration by parts. So remember how that goes. So you pick so the integral of u dv equals uv minus the integral of v du, right? So remember that is kind of that's the formula to recall. And so let's set u equal to y, then du is equal to the derivative of y, which is dy. And dv, let's set that equal to e to the negative y dy. And so the integral, so v would be equal to the integral of dv, which is negative e to the negative y. Okay. And so we can just use that down here. Okay, and so when we do that, what do we get? Well, just kind of plugging in, remember this is the form u times v minus the integral of v du. And so we get negative y e to the negative y minus the integral of negative e to the negative y and then dy. Okay, and I'm kind of writing this in this way, right? So we have to calculate this integral and then we'll evaluate it. All right, so we can clean this up just a little bit. We get negative y e to the negative y, and then I'm going to write plus the integral of e to the negative y dy. from 0 to infinity. And of course, that's very similar to what we saw before, isn't it? So negative y e to the negative y, and then it's minus e to the negative y. And this time we evaluate from 0 to infinity. Okay, and it's really the same story as before. So we can plug in, so that's a minus there. So we end up with basically 0 minus 0, 0 minus 0, minus 0 minus e to the negative 0. Okay, and of course we get a 1 there. Right, this is 1, everything else is 0. And so for gamma 2, the value is 1 also. Now, it turns out that, there is a nice pattern to these, but, they don't always equal 0. Right, but you could go on further and say, well, what's gamma 3? That's integral from 0 to infinity of y squared e to the negative y dy, right? You get something. All right, you'd end up with 2, actually. So what are the values of this? Well, so gamma 1 we saw was 1. Gamma 2 we saw was also 1. Gamma 3, it turns out, is equal to 2. Gamma 4 is equal to 6. Gamma 5 is equal to 24, right, and so on. We could keep going. So the pattern actually, what the pattern actually is that, so we start with gamma 1 equals 1, and then gamma alpha is equal to alpha minus 1 times gamma of alpha minus 1. Okay. Right, so for example, for gamma 5, that's equal to, just using this, that would be alpha is 5, so 5 minus 1 is 4. Right, so it would be 4 times gamma of 4. Well, what's gamma of 4? Well, gamma of 4 would be 3 times gamma of 2. I'm sorry, gamma of 3. Well, what's gamma of 3? Well, gamma of 3 would be, so you got the 4 and the 3. Gamma of 3 would be 2 times gamma of 2. Okay, and what's gamma of 2? Well, bringing the 4, 3, and the 2 forward, we get 4 times 3 times 2, and then it's going to be what? 1 times gamma of 1. So each time I'm just applying this rule, right? So gamma of 3, that's this part here, is that, right? Right, and then so of course gamma of 1 is 1. So this is 4 times 3 times 2 times 1 times 1. Okay, and so as you can see, in general, gamma of alpha is just going to be alpha minus 1 factorial, where if we, we're assuming alpha is a positive integer. I.e. non-negative. Okay, and so that's the gamma function, right? So it really, if your alpha parameter is an integer, it's very easy to evaluate the gamma function just using basically this formula here. You don't have to use the integral. Okay, so let's talk through these parameters a little more. What is the alpha parameter? The alpha parameter is called the shape parameter. Okay, it's called the shape parameter. It's going to tell you, it's going to give you the general shape of the gamma distribution. Is it going to look more like this, or is it going to look more like this? How's the, maybe it's really steep, right? So this is what the what the alpha parameter tells you when you're looking at the distribution, the gamma distribution. The other parameter is the beta parameter. Okay, the beta parameter is called the scale parameter. Okay, it's the scale parameter. And so for beta equals 1 and alpha varying density functions, let's draw a picture just to kind of get a sense for this. So here we're going to set beta equals 1, and we'll let alpha vary a bit. Well, just 3 examples. So when alpha is equal to 1, the gamma function looks like this. Okay, remember this is 0. Now when alpha equals 2, you start to get this like bump in here. So it looks kind of like this. Now when alpha equals 4, meaning we kind of move it over a little more, you can see the skew sort of gets pulled out. I mean, the hump kind of gets moved to the right a bit more. So in general, we'll use values of alpha that are integers. Now, if alpha is not an integer, then the PDF, the density, the integral, does not have a closed form expression, and in those cases, you'll have to use tables. So we will, in general, use integer values of alpha. Okay. And really, like in practice, that's almost all you need. I shouldn't say that because there are lots of examples where you don't need it, but in practice, for the most part, it is sufficient. Okay, let's take a look at the mean and the variance here. So if y is gamma alpha beta, okay, then the expected value of y, the mean, is just equal to the product of the parameters. Nice. And the variance of y is equal to alpha times beta squared. Amazing how simple that is. Okay. Now, in probability theory, the gamma distribution is sort of the more general distribution, but there are a couple of special cases, really 2 of them. 2 special cases of the gamma distributions that come up a lot in probability theory. The first one is what's called the chi-square distribution, and it's an example of a gamma distribution. So let's take a look at this. We'll define it first. Definition. So we're going to let nu be a positive integer. This looks like a v. It's called nu, and nu be a positive integer. Then a random variable y is said to have and this is the chi-square distribution. So a random variable y is said to have a chi-square distribution if and only if y is gamma alpha beta, where alpha is equal to nu over 2. So it's basically it's a positive integer divided by 2, and beta, the scale parameter, is equal to 2. Okay, so we just said that in general we would use integral values of alpha, but not always, right? So here's an example of the not always. This is a highly valuable distribution, as you'll see, especially when you get into mathematical statistics. The chi-square distribution is everywhere. It is essentially a gamma distribution where the beta parameter is 2 and the alpha parameter is some integer, positive integer, divided by 2. Okay, and so we'll frequently refer to this using the notation chi-squared. So the chi-squared distribution comes up a lot in statistics. So you may have seen it if you've taken an elementary statistics class, actually. The expected value here of the chi-square distribution is equal to nu. Oops, I wrote 2 equals there. Okay. Which we know is equal to twice alpha, right? Nu is, alpha is nu over 2, so just doing a little algebra there, nu would be 2 times alpha. And of course, beta is equal to 2, so this aligns with the expected value of a gamma distribution, in that it's alpha times beta. And the variance of y here is 2 times nu, okay, which of course is 2 times twice alpha, which is equal to alpha, and then 2 times 2, that's beta times beta, so beta squared. So again, variance is 2 nu, the mean is nu. Okay, and so this is the first really big application of the gamma distribution. It's going to be the chi-square distribution. Okay, now the other one, I said there were two. The other one is what's called the exponential distribution. Let's define that quick. You'll see that these are just special cases of the gamma. So a random variable y is said to have an exponential distribution. An exponential distribution if y is gamma, alpha, beta, where alpha is equal to 1 and beta is any value greater than 0. Okay. In these cases, the density function is going to kind of simplify down to this. So it's 1 over beta times e to the negative y over beta, or 0. And this is for 0 less than or equal to y less than or equal to infinity, and this is otherwise. Now hopefully that makes sense if you remember back to what the gamma distribution looked like. All right, just pulling this forward from the previous page. If beta is 1, if alpha is 1, then this is 1, right? So this would be 1, and this here would also just be beta. Okay, and then this this is equal to 1 also in the case of alpha equals 1. Right, so you're really just left with this over that. Okay, and so that's what we see. It's just a simpler version of the gamma distribution. All right, and so the expected value of y in this case is going to be beta. Right, it's really just alpha beta, but alpha is 1, so that's fine. And the variance of y here is beta squared. Right, it's really alpha beta squared, but again, alpha is equal to 1. Okay, so that's an example of the exponential distribution. And both of these, both the exponential and the chi-square, are just special cases of gamma. So that's kind of the key here. A key idea is exponential beta and chi-squared nu beta are both special cases of gamma alpha beta. Okay. Oh, sorry, this is chi-squared nu. There's only one parameter. Beta's fixed in that case at 2, remember. Okay, so for the exponential, you really just need to know the beta parameter because the alpha parameter is fixed at 1. And for the chi-square case, you really just need to know the value of nu. You divide that by 2. That's your alpha in the gamma distribution, and beta is fixed at 2. Right, but these are both just special cases of this guy. Okay, let's do an example or two just to see some cases where this is useful. Right, so, example. We'll just kind of set the scene here a little bit. Let's suppose that emails arrive at a help desk at an average rate of 1 per hour. Suppose emails arrive at a help desk at a rate of 1 per hour. Okay, and we assume independently over time. Okay, so this is actually an example of what's called a Poisson process with a rate of lambda equals 1. Right, so this is actually called a Poisson process with a rate of lambda equals 1, meaning there's one occurrence per time interval. Right, now we haven't discussed this, but I'm just this is a little bit of background and just kind of shows how some of these different probability models can be connected. It turns out that if we have two separate Poisson arrival times, like x1 and x2, then their sum is going to be a gamma. So if we have two separate Poisson processes, and we'll say x1 and x2, then their sum, okay, basically y equals x1 plus x2, that sum is actually going to be a gamma distribution, a gamma random variable, right? And in this case, alpha will equal 2, right? That's what corresponds to the two random variables, and beta will equal 1. Okay, and so let's say our question is, what is the, we're interested in the random variable, the arrival time until the second email, right? So let's let y equal the arrival time of the second email, okay? All right, so then, y is gamma to 1, as we just said. So what's the probability, what's the probability that the arrival time of the second email, i.e. y, will be less than 4 hours? That's a good question. Okay, so y is a gamma random variable. So what's the PDF look like here? So f of y, what's the density function here for a gamma random variable that is alpha 2, beta 1? Well, we can just write it out here. The thing is y alpha minus 1 e to the negative y over beta divided by beta to the alpha times the gamma function evaluated at alpha. Right, and so if alpha equals 2 and beta equals 1, then what do we get here? Well, we get basically something much simpler, right? So alpha is equal to 1, or sorry, alpha is equal to 2. That means we keep the y, and then we also get e to the negative y over 1. These guys down here are both 1, aren't they? Okay, and so we end up with just y e to the negative y, and this is going to be valid for y greater than 0. Okay. All right, and so what we're interested in is the probability that y is less than 4. And so that's a simple integration, right? We take the integral from 0 to 4 of basically just our y times e to the negative y dy. Okay. And this is equal to, let's see, it'd be negative y plus 1 e to the negative y, and that's going to be from 0 up to 4. Okay, and so we can easily evaluate this. That's going to be negative, and then it'll be, what, 4 plus 1 e to the negative 4 minus negative 0 plus 1 e to the negative 0. Okay, and so this is 5e to the negative 4. And what is left here is just 1, right? Yep, so plus 1. And what do we get? Well, technically, hold on a second. This should be negative 5. Yep. So negatives out front there. And so this would be, let's just write this as 1 minus 5e to the negative 4. And really, when you crunch all of that, you should get something like 0.908. Okay, so there's about a 91% chance of the second email arriving within 4 hours. That certainly squares with intuition. We expect 1 an hour, and so we definitely would expect, with high probability, that we would get 2 within 4 hours. So, all right, very good. Let's see. Let's do another example. Let's say that y is the time in hours until the first email arrives. Okay, time in hours until the first email arrives. Well, I mean, by the same kind of logic, this is going to be a single Poisson process, and so we would just kind of decrement the parameter a little bit. So in this case, y is going to be gamma, alpha equals 1, beta equals 1. Okay, and I think, is this one that we plotted? Yes. So this is one that we plotted earlier, if you remember. We kind of plotted what this density function looked like, and it looked like this. Right, so meaning like the highest probability is definitely early on here, right? And it trails off quickly. This trails off really quickly. I don't have numbers on the x-axis, but it trails off very, very rapidly. And so this is kind of what the density function looks like. It makes sense because how many hours do I have to wait until the first email arrives? Well, they arrive on average 1 per hour, so I would expect 1 pretty quickly, like within an hour, maybe 2 at the most, right? Like it's going to get here pretty quickly. And so this is the density function, and that makes sense. And so what's the PDF look like here? Well, just kind of plugging alpha and beta into the generic gamma function, we would see that this will look something like 1 over beta e to the negative y over beta. Okay, and that's just, in this case, beta is equal to 1, so this is just e to the negative y. Okay, for y greater than or equal to 0. All right. And so this is an example of an exponential distribution, isn't it? Alpha is equal to 1, right? So alpha equals 1 means that we have an exponential distribution. And so the probability that, what's the probability that y is less than 4 in this case? The probability that y is less than 4 hours. In this case, we're talking about the probability that the first email arrives within 4 hours. Right, and so that's just going to be equal to the integral from 0 up to 4 of e to the negative y dy, and that, of course, is equal to negative e to the negative y, evaluated from 0 up to 4. And so I get negative e to the negative 4 minus negative e to the negative 0. So 1 minus e to the negative 4, and so this is approximately 0.982. So about 98.2%. All right, and so that's an example of using the gamma distribution. Now the idea with the gamma distribution, remember, is it's going to describe probability distributions that are continuous, they're not symmetrical, they tend to have big, long tails to the right, they're censored at 0, meaning no values below 0 are allowed for the random variable. They're going to have 2 parameters, alpha equals 1, beta equals 1, or sorry, alpha and beta, not necessarily equal to 1. 2 special cases that are highly useful are the exponential distribution, here's an example of that, and the chi-squared distribution, which we didn't see an example of, but it is a highly useful in mathematical statistics and just statistics in general. So we'll get into that later. We'll see lots of examples of that. All right, so we'll end the lecture there, and up next we'll discuss briefly the beta distribution. All right, until then, take care.